Exactly.
They're pretty easy once you get started. But once you can ignore the audience.
Yeah, once you just like start having fun with it, I think.
Again, I'll try not to run over or happen. It'll probably be about that.
I mean, I guess since we don't have a server,
It's not gonna hurt anybody.
where do they have to go?
Well, I did pare back some of the stuff I was talking about.
I think it'll be good.
Steal your thunder. Oh.
Audio. Sounds good. Like if you
Oh,
just walk
okay.
out there.
Are you gonna introduce?
Testing, testing, 1, 2, 3. Live stream test specifically.
When do we start? Whenever I want to.
I think whenever she starts to
Oh. So doesn't she talk and start the trivia?
she does.
What? Oh, she's got her own headset. Oh, it's so hot. It only makes it so long. I know. I'm ready to go. Where'd she start? What's up?
We usually start about 5 minutes late.
Okay.
And if you'll just turn the mics off, just for battery's sake.
right, I think we'll go ahead and get started. Thank you so much for being here on this mostly cloudy night. Luckily, you're going to hear a talk that's going to show so many really beautiful, incredible images of space, so it will be almost like we got to observe tonight. My name is Amanda. I'm a lecturer in the astronomy department. I'm also the outreach coordinator. Most astronomers do it in part because they love sharing it with people. So thank you all so much for being here. It really makes the work that we do worth it. This is the first talk of our summer series. We're, as always, going to start with some trivia. I'll tell you the dates for our other talks in the summer. Fingers crossed we'll have better luck with the weather then. Then we'll hear from our two fantastic speakers, and we'll do Q&A. So we'll first start with trivia. How trivia is going to work, there are 5 questions. These are multiple choice questions. I will give you some time to think about the answer. Collaboration is strongly encouraged. Talk to the people around you. Even if you didn't come with them, meet someone new. Then I'll say 3, 2, 1, vote. And at the same time, everyone will show me 1 if you think it's A, 2 for B, 3 for C, 4 for D, and 5 for E. That way I can survey the collective knowledge in the room. All right, is everyone ready? Yeah. Woohoo! Okay, our first question, we're going to ease you into it, so don't stress. What is the most abundant element in the universe? So think about it, talk to folks around you, see if you're on the same page. All right, I'm not going to give you a lot of time for this one. Let's vote. 3, 2, 1. Yes, it's unanimous. We've got a lot of ones. Hydrogen is the most abundant element in the universe. In fact, most of it was made during the Big Bang, so almost 14 billion years ago. So think about that while you drink your water, H2O. All right, we're going to get a little harder now. So we're focusing on hydrogen. Hydrogen, like light, has a spectrum, so we can look at its spectrum. And who was the first person to observe the hydrogen spectrum? All right, lots of good discussion. I didn't know this one myself, had to brush up on my history of science. But let's vote. 3, 2, 1, vote. All right, I see some 2s, some 5s, some 4s. Do I see a 3? Do I have a 3? Yes, I have a 3. All right, we do not have consensus on this question, which means we're going to learn something. It is angstrom. Yes, so even though Jalen Brunson has done so much for society lately, he was not the first one to look at the hydrogen spectrum. And angstrom, we said it was in this picture, it is the A with the circle above it. So that is the unit of measurement called an angstrom. It's 10 to the negative 10 meters. So that is very, very small. All right. But with astronomy, we work with things on all scales, really, really small to really, really big. So let's think about scale for this next question. The wavelength of hydrogen alpha, which you'll learn all about tonight, is as long as which of these?
I just guessed.
You will find out. This is your little teaser. A type of hydrogen. We had a great question up front. What is H alpha? I'm just going to say it's called hydrogen alpha, and our speakers are going to really expertly explain it to us. So this is a little teaser. All right, but let's go ahead and vote. 3, 2, 1, vote. All right, I see 5s, 1s, 2s. Again, do I have a 3? Oh, a 3. And I see 4s. Okay, so once again, we're going to learn something because we don't have consensus. And it is 10% of a red blood cell. So very small, but still a little bit bigger than 20 atoms. So it's something that a microscope can measure. All right, question 4. We're going to stick now on the theme of H alpha. So we can use H alpha to look at different objects, and that's what our whole talk today is going to be about. But we could also look at the sun and only see the H alpha coming from it. So which one of these images shows the sun with just H alpha coming from it? The astrophotographers in the room have already put up their answers. They're feeling very confident. All right, we've already got a lot of confident people, so let's vote. 3, 2, 1, vote. All right, I see 1s, 4s, 2s, 3s. There's no 5 this time, so don't see that. And the answer is D. So our sun emits at all different wavelengths. Here we have it in the radio light, visible light, so what our eyes would see if you're safely looking at the sun. UV, ultraviolet light, and then hydrogen alpha. All right, you guys are doing great. We have one last question for you. Which of these were discovered thanks to citizen scientists and astrophotographers? We have Tabby's star, the Donatello 5, 6, 7, 8, and 9 galaxies, the Soap Bubble Nebula, Comet Lovejoy, and the Giant Squid Nebula. All right, 3, 2, 1, vote. I see lots of 4s. I see 5. I see a 1. I see a 2. I see a 3. Congratulations, you are correct. It is all of them. So this is a really important reminder that so many people contribute to the field of astronomy. It is not just folks who have graduate degrees in astronomy. Humans have been staring at the sky and making note of it for thousands of years, and that tradition carries on. And that is what brings you all here tonight. So we have 2 other talks this summer, July 24th and August 28th. They're both at 8 p.m. so that it would be dark enough if it's not cloudy. So we really hope we got a not cloudy night. But until then, I'm going to hand it off to our first speaker of the night, Sean Walker.
Is this on? Okay. Thank you very much. I'm going to dim the light so that it's easier to see what we're going to be looking at, because a lot of the stuff is kind of faint. Anyway, so I'm Sean Walker. My day job is I'm a senior editor for Sky and Telescope magazine, and we write all about astronomy, and it's really cool. And if you want to check us out at the end of this talk, I have a slide so you can scan it and check us out. But let's get on with this little project here. It's funny that that she was mentioning that all kinds of people get involved in astronomy. My day job is an editor for an astronomy magazine, but my degree's in painting. Anyway, so what I'm here to talk about is a project that me and a couple of my friends embarked upon about 10 years ago, which is called the MDW Sky Survey. And it's a partnership between 3 amateur astronomers, myself, Dennis DeChico, and David Middleman. Anyway, we got together several years ago with an idea to map the entire sky in hydrogen alpha light. Now, she was mentioning, hydrogen alpha light. Now, hydrogen alpha is hydrogen, and the most predominant molecule or element in the universe. It's basically the building blocks of everything. Now, the gas is left over in our galaxies, and that's what stars are made of. I don't know. Mapping hydrogen alpha also maps where star birth occurs, and star death. We'll get into that in a few minutes. Our project goal was to map the entire sky at a very small image scale, which is 3.17 arc seconds per pixel. All right, that might not mean much to a lot of people, but it's way smaller than one crater you see on the moon from Earth. Okay. It grew out of several interests of ours. Okay. Dennis and myself, working at Sky and Telescope since the early 2000s, we were into wide field imaging, and as digital detectors were growing at that point, this opened up a lot of opportunities to be able to take large, wide-angle images of the sky, as opposed to in film where we would have to contend with, one single exposure versus using digital technology. You can take a bunch of short exposures and add them together. And that's useful because, you can quantify all the data, but you can also eliminate variables like satellites or airplanes flying by, which, as we know, is a big growing problem. Our first project was mosaicing a 15-frame portrait of the sky spanning about 4,000 square degrees, or 10% of the entire sky, that we published in April of 2009 in S&T. If anybody's familiar with the sky at all here, the central object over here is the Orion Nebula. All of the constellation of Orion, right over here. And here's Taurus, there's the Pleiades. This is the California Nebula, and it doesn't really look like that when you go deep enough like this. So this is the kind of stuff that really excited us. To give you an idea of how big that is on the sky, this is an all-sky photo taken with the fisheye lens with our result, mosaiced into the field. Later on, because we were using a low-resolution camera lens to do that, we decided to step it up with a larger camera lens. We went to a 110 millimeter lens and a larger CCD, and started imaging the same area at a better image scale. So this is how we managed to expand upon it. And the point of getting with, I was getting to with the larger image scale is that When you use a bigger optic, the stars get smaller, and therefore you're revealing more of the gas around it. And you'll see a big difference when we get to our survey in a few moments. All right, but what was really impressive here, you know, we went even deeper, and you can see all this faint nebulosity going way out here and beyond the Pleiades and whatnot. And also, this is the band of the Milky Way passing through. There's Auriga, there's Taurus over here, but this is Monoceros, all the way down to Puppis and Canis Major down at the bottom there. Here's a zoomed in a little bit more. To compare the two, as I was telling you, here's a 50 millimeter camera result, and the whole thing posted over the house that my coworker Dennis had shot all of this. This is actually to scale. If you could see the sky with just your naked eye and hydrogen alpha, you'd see all this gas. I think last summer you guys shared a picture of our survey mosaicked over the Manhattan skyline. This is the exact same kind of thing. That really shows you how deep this goes. I pushed the data so you can see all this really faint extraneous stuff. Sorry about that, I hit the wrong buttons there. Going farther out than even what you were seeing in the Milky Way band there. Anyway, in 2015, Dennis, myself, and our friend David Middleman were kicking around ideas of how we could expand on this work further. First, we experimented with a much larger telescope. We moved from a camera lens to, it was a fairly small camera lens with the 150 millimeter focal length, to a 200 millimeter lens with the 500 millimeter focal length. And that, again, makes the stars a lot smaller. So we tested this out and made a 30 panel mosaic of Cygnus. So it's a much higher resolution than the earlier projects that we were doing. And it revealed a lot of great stuff in this area here, including, as you see over here, this is the Veil Nebula, and all of this is over here in the middle of Cygnus. There's the North American Nebula, and over here is the Crescent Nebula. It was kind of neat. Here's a good example again of the difference in the resolution. With the smaller telescope, you're able to, you see a lot of this faint filamentary nebulosity. Anyway, the results were promising, but there was a couple of limiting factors. We were living in New England, and you're not too much better here in New York. The skies are really bright. All right. Also, our weather isn't great up in the New England, so getting multiple nights of data is sometimes challenging. All right. The detector we were using exceeded the specs of the telescope we were using, so the stars were really distorted in the corner. And then, you know, reflective optics, I said, they require minor recollimation with changing temperatures over the course of the nights. So we kind of eliminated that. While regrouping to discuss the results, Dave suggested that we not limited ourselves to just a certain region of the sky. We could perform a systematic survey of the entire sky shot remotely from a dark sky location using off-the-shelf technology. Now again, none of us are professional astronomers, but the technology is available to anyone nowadays to, you can become an astronomer yourself. Just buy the equipment and learn how to use it well. Anyway, one of the inspirations for Dave's idea of, like, you know, we shouldn't limit our project to just one certain area of the sky is that all the H-alpha surveys were fairly low resolution at the time. This is probably the best map that was available. It's called the Virginia Tech Spectral Line Survey, and Southern, I can't see the text there, H-alpha survey. I don't know why we're missing that. Anyway, it's called the Finkbinder survey, and it has a low resolution map of all the nebulosity that you can see. But as you'll see in a moment, we far exceed that scale there. So David was already a member of New Mexico Skies, and that's what's called a telescope farm. There's these places that have cropped up over the past decade where amateur astronomers can send their telescopes when you live in, like, Manhattan, and you have really bright skies, you can send it to this area where it's in the middle of nowhere, and there's some people there that will mind your equipment and take care of it if there's a problem, and that's how you're able to work these things from a distance. So he's already had built a couple of observatories at different facilities around the country. He did the Milliman observatories in Vermont, at Middlebury College. Let's see, Hutt Observatory, and a few other ones. The Yellow House was his place in Dover. Okay. But, okay, that lists most of them again. Anyway, he has quite a few different telescopes. This is David in the groundbreaking of one of his observatories. This is actually at the place that we shot most of our data in New Mexico. That's one of David's projects, which was moving a 36-inch Buller's telescope from, I believe he picked that up from Yale University and moved it down to New Mexico, and he was restoring it and putting it to work in modern times. To give you an idea how big that instrument is, this is one of his friends working with it. Yeah, 36-inch telescope is pretty big. But anyway, so the planning for our survey commenced in the fall of 2015. We settled on 230 millimeter. That's about a 5-inch aperture refractor, okay, as our primary instrument, and two 16803 CCD chips. That's kind of jargonese for, they're a very large chip. If you remember 35 millimeter film, that gave you a 35 by 24 millimeter frame, okay? This was, I believe these are 36 millimeter square, or 38 millimeter square. It's a lot bigger area of the sky. Anyway, but again, as we were saying, we were shooting at 3.1 arc seconds per pixel from New Mexico skies. Dennis, whose speciality is building stuff as a mechanical engineer, he went to work on designing the rigs. The focusers on these scopes are a little different than a regular telescope in that it's not just a rack and pinion that you move back and forth. He replaced them with a device that just moves it a very tiny bit amount, because these telescopes were only designed, we were designing them just to image, so we're not putting eyepieces in their place. So, and then instead of a filter wheel, because we were only concentrating on one wavelength of light, we decided to hard mount a single filter right in front of the detector. And that eliminates any issues of dust accumulating between the elements, and it really causes problem night to night if you get dust on your system. You have to calibrate, it's called the diffuse calibration. And what happens if a piece of dust gets on your detector and you image on it, it makes a dark spot. But if you record an image of an evenly illuminated surface, let's say an electroluminescent panel or whatnot, it maps that imperfection, and you can subtract it from your data. So, and that's how you get clean images out of that. All right. So this is Dennis is putting together this system. He has a full lathe and workshop in his basement. This is the filter as we were talking about, hard mounted, rather than having a filter wheel. And this is one of the prototype scopes as he assembled it, and we were testing it. Like I said, the focuser down at the bottom here is really kind of special because it seals the whole system, and we don't have to deal with dust, especially when we were planning on sending our scopes to New Mexico, which is the desert, and it's pretty dusty. Oh, there we go. That's the back end of both the scopes. We started off with 2 scopes in this survey project, and they seem to take care of the job for quite a while. Planning and executing, required custom software too. At the time, when we started this a decade ago, there wasn't a lot of options for being able to point a telescope to thousands of different fields accurately each night and be able to return to them quite frequently. We settled at the time on a program called ACP. It's called the Astronomer's Control Panel for remote control of all the observatory's function. That was really great. Today, the software has been retired, because there's a lot of better options. A lot of things happen in a decade, especially in technology. So, first test using the our planning software with the SkyX revealed a big flaw in its programs, where this program had a built-in mosaicing feature, but it didn't consider the sky as a three-dimensional object. It looked at it as a flat surface. And as you build a mosaic from a central point in that, you encountered the distortions in the sky. And as you see it, as we were moving away from the central point in our tests, we were developing these large gaps. And that was the problem between looking at the sky as a two-dimensional plane versus a three-dimensional sphere. So we went back to the software developer, Steve Bisk at Software Bisk, and asked him to rework his mosaicing feature. And he went back and did it. Within about 2 weeks, he came up with a great revision to it. So now we were able to plan out exactly where we were going to point our scopes and how we would be returning to these fields. We ended up with about, we'll see in a moment, several thousand of it. But this is an accurate map of how we approached our project here. Anyway, the entire sky turned out to require 4,120 fields, each consisting, our goal was 4 hours of exposure, but as I mentioned, unlike film, we could take those in smaller batches. So we decided to do 12 20-minute exposures of every field. And that gave us enough so that we could subtract out variables like satellites and other objects like that. Yeah. 3,180 of those fields were accessible from New Mexico skies, down to about 33 south, okay? That's quite a bit of the sky. About 2/3 of the sky, actually. After months of testing, we began operations in May of 2016. And these are the scopes in operation down in New Mexico. The things you see on the front are those electroluminescence panels that I was telling you about. Those cover the scopes during the day, and they're actually illuminated, evenly illuminated. We use those to take flat fields. Now here's the scopes with one of our former collaborators, David Saliski, on the grounds there. The two in the front are survey scopes. The one in the middle in the back there is a smaller scope that we use for follow-up observations and occasionally shooting some color images. As you saw earlier, these scopes are monochrome detectors, and they're only going to record one wavelength of light. So pretty much all of our images are black and white. By March 2017, we had accumulated a pretty good amount of data, enough that I could show off, stitch together a bunch of the fields, and you can get a really good idea of how this project is going. What you're seeing here is, basically 3 seasons across the sky here. The objects over here are in the summertime. That's Cygnus, and there's the Veil Nebula again. This is more things in the fall and towards the winter. There's the winter Milky Way, and there's Auriga and the Gemini and just the tip of Orion over there on the right. To give you an idea how the depth of this of our project was going, I was stitching together images around a popular object called M31. That's this galaxy over here. And I was noticing all this nebulosity around it that I never see in anybody's pictures, okay? So I stitched this together, and I shared it with a website called the Astrophotography Photo of the Day. And that helps promote, it spread really cool stuff about astronomy every day. If you go to APOD, you can see a new picture every day that you'll learn something about astronomy. Anyway, this made APOD on March 3rd of 2017, because not many people knew about this stuff. The time span for this project was estimated to be about 5 years. Yeah, that was that was pretty optimistic. Anyway, turns out that was underestimated by about a half. We only just finished this earlier this year, so 10 years it took us to accumulate all this data. And it's about, I have about 9 terabytes of data, but there's a lot of a redundancy in that for different reasons. I think the whole thing is about 6 terabytes in all, actually. Unfortunately, we lost David to brain cancer in May of 2017. His wife, Michelle, really wanted to bring all of his projects to fruition and asked us to continue on, and we were happy to do so. My coworker, our colleague and partner here, Dennis DeChico, also had discovered a lot of asteroids in the late 90s when it was fairly easy for amateurs to make discoveries like that. And he named one of the asteroids that he discovered for David. Due to the nature of our pointing script, we don't target one field at a time and focus on it until it's done. We only targeted objects when they're highest in the sky each night. So that meant that some fields could take months to years to complete. So we have a long baseline in between some of our fields, and that's really interesting because you can use it for doing some really exciting science that Nor will be getting into later on. All right. Our initial project, though, was an aesthetic project, but we knew if we pursued it with scientific vigor, we'd be able to, people with more experience and knowledge than us would be able to extract a lot more data than it. And that's how we ended up with Columbia here, and I'll say in a few minutes here. Here's a couple of our results in the northern hemisphere here to give you an idea. All right. This is a big nebula in Lacerta. I think that's called SH2-127. There's a lot of great names like that in astronomy. Okay. To give you an idea how big that object is, this is the entire constellation of Lacerta. All right. It's a good, sixth of the whole constellation. If you're not familiar with Lacerta, not a lot of people are, it's right next to Cygnus. You'll see it in a minute. Here's a comparison also to give you an idea of how this was when we shot this particular region of the sky. This object is a supernova remnant called Simis 147. This was taken with our 110 millimeter lens that we did in 2010, all right? And with our survey, it really, with the larger aperture, the stars get smaller and you're really able to see more of the nebulosity around it. Of course, it also helps that we shot for an even darker sky. All right, this is a comparison between that ThinkBinder survey, and our data of the same object, the Simis 147. To give you an idea why we went and did this, because you can see a lot of tiny stuff that wasn't available before. Here's another comparison. This is an object called IC 1396 at the top left here. And the other object is SH2-129. These are both in Cetus, okay? 129 is virtually non-existent in the ThinkBinder data. Last time, this is another area. This one's at the border of Gemini and Orion. The object at the top right there is NGC 2174. And, the objects down at the bottom left here are IC 443 and IC 444, which were in some science news last week in that those two objects are actually overlapping supernova. And a big paper was just published about disentangling which is which. This is an object in Canis Major and Monoceros right at the border there, maybe Puppis. It's called the Seagull Nebula. And it definitely looks like a bird with its wings way out in H alpha here. This is actually a whole constellation. I'm not sure anyone's going to recognize it, but do anyone want to make a guess? Okay. The bright star here in the image here is Vega, or Vega. It's up in, right now, after dark, okay? It's one of the brightest skies in the northern sky, all right? In the constellation of Lyra. And this is the entire constellation of Lyra. Oh, let me go back a second. To show you all this nebulosity that's permeating the area here. Let me go a step forward one. This is zooming out with even more panels. It gives you an idea of how these bow shocks or whatever seem to, reach around into the from one region of the sky to the other. It seems all connected. All right, and this is to give you an idea. Here's Cygnus and Lyra at the top here to give you an idea of the scale here. There's that object at the bottom that I showed you in Lacerda at the bottom left earlier. Right. This is the constellation Sagitta, which is in just south of Cygnus here. And what's kind of interesting here is the cluster. I think it's a globular cluster called M71. It's surrounded by this nebulosity here, and you'll see it in a second. Yes, this is the whole region, and it really shows you that this cluster might be carving out the nebula, dissolving all the nebulosity in this area here. Here's another object called, I believe, the Cedar Bald 214 up in Cepheus, I'm sorry. And to put that in perspective, there's that same object at the top right of the field. But this whole panorama covers all of Cassiopeia and Perseus and several objects here that are, if you've ever looked through a telescope in the north, you've probably looked at the double cluster. And that's an object right here. You can see it from here, and if we were observing tonight, probably would be looking at it too. That double cluster, as I showed you earlier, is also surrounded by faint nebulosity too. These are definitely the nebulosity was the elements that gave birth to these two star clusters, and they are now burning up, or evaporating the nebulosity in the area. As the stars get hot, they interact with the medium around them and dissolve some things. Anyway, here's that object that I pointed out earlier, the Veil Nebula. Okay, another interesting thing about our survey data is that it resolves a lot of small-scale features, but you can also do a really nifty thing with modern software, which is to remove the stars and see more of this nebulosity. So that's what this area looks like without any of the stars in the field. It really brings out a lot of these bow shocks that you didn't see before, like over here, and this really interesting curvy bow shock front, I believe it's called. This is another object called Sivian 2, which is up in Cassiopeia on the border with Andromeda. And this object was discovered in 1972 and not photographed since. I saw it on our data, and it took me a long time to research, what is this? And we finally found it in a paper published 50 years ago. Here's another point of view of like going a little further to the west here, east or west. And this is right in the border of Cassiopeia and Camelopardalis. The big object here is like, what's interesting here is there's a star that's plowing through the medium, one of the brightest stars in Camelopardalis up here, and it's creating this bow shock as it's passing through the nebulosity in the region. And here's what it looks like when you get rid of the stars again. Here's that object that I showed you earlier, IC 443 and 442. What's interesting here is that it's a supernova, two supernova remnants actually, and it has a very big envelope that's very rarely seen. And when you blow out the data here, you can really start to see this faint outer halo of the object here. I think I did it. Oh, here we go. It really shows you all this stuff is somewhat related. Here's a region in near the center of our Milky Way. It's hard to tell here, but this is the Eagle Nebula and the Omega Nebula down here. Here's another area that has that surrounding faint shock front, basically, from the brighter stars in the center of the area, the young stars that are born in these star-forming regions. This is that California nebula that I pointed out earlier, which doesn't really look like California in H-alpha. I like to call it the Scimitar Nebula. And here's Central Cygnus with the Crescent Nebula, and you can't see it in here, but that soap bubble nebula that she talked about from Discovery was discovered by one of my friends in 2009 or 2010, in that he was taking pictures of the Crescent Nebula, and there was a little spot that looked like a dust mote that wouldn't come out of his images. And most people, had been looking right past it for years, and he was the first one to go, hey, isn't that something? Anyway, here's all of Cygnus again. That's the entire constellation, actually, with the borders cropped properly. This is to give you an idea of the image scale, really, on our survey. This shows you the full resolution. This is the Crab Nebula in Taurus, and it gives you a pretty good idea of that. You can resolve a lot of really small-scale features, and we've made a lot of discoveries with this project because of that resolution, as we'll see in a moment. This is NHL, part of our survey here. This is a galaxy called M83. It's a popular galaxy. And I'm here to show you that there's a lot of gases in other galaxies. This is where stars are formed, and other galaxies, nearby ones particularly, are loaded with these star-forming regions. Yeah. The image scale of the survey lends itself to revealing large-scale structures that aren't visible with lower resolution instruments, as I've been alluding to. While assembling several of these fields in northern Cepheus, I had noticed a bow shock that continued over through several fields, so I stitched it all together here. And as you can see, this big object here going up and down in this area here. I sent the picture to Dennis, and he did a lot of research to be able to figure out what it was, and we were able to name it, which is the suspected supernova remnant, as the last paper that discovered it showed. It has a name, G107. Really sexy name, huh? Anyway, by the way, these names are generally coming of these supernova remnants. They come from their galactic coordinates, so that's what the G stands for, and the number following it. That's based on, it's different than right ascension and declination. Anyway, our image was the first object of the image of the object recorded at optical wavelengths, and our data was bright enough to allow astronomers to be able to target some of the brighter regions for spectroscopic study, and they were able to determine, yes, indeed, it's a supernova remnant. All right, and it allowed us to be part of the discovery and verification of this object, which was kind of a really big deal for me. I'd never really discovered something before. All right, so it went on. We worked with Robert for a few different of these discoveries because he was really interested in these. One of his big interests was high galactic latitude supernova remnants, which means supernova remnants that aren't just in the plane of the Milky Way. Here's the paper that was published on the findings. Anyway, so we had several of these. I won't show you the papers afterwards, but here's another one called G70. I'm going to skip the long part on it. Here's another one. This is a really interesting object called the Ursa Major arc. And it's just this big faint bow shock in Ursa Major, okay? And it's really huge. I'll show you how big it is. It's easier to see here in the negative. These are just the fields that I was able to detect it on. And lately, this is with our completed survey data. This gives you an idea. This is a 20-degree field of view surrounding Polaris, the North Star here, right? And here's our arc going right across the field here. It's roughly 30 degrees long. Also, we've discovered several planetary supernova remnant discoveries. See this big arc going around here? This was reported that I did some follow-up observations of. But when I was doing that, I happened to notice that there's another object right over here, and that's this thing right here. This is a different nebula that was well known. And what's interesting, so I zoomed in on that field, and it was a little hard to see, but 3.17 arc seconds helps reveal a lot of faint structures, but as I said earlier, when you remove the stars, it helps to really reveal some of these other things. So I was able to find this object here. And here's a color picture that we did. This ended up, being a paper in on several supernova remnant discoveries. Here's another big feature that I was really interested in that we went to earlier. It's the Orion Eridanus bubble that I had shown you that we had targeted with our first projects. This gives you an idea of really how well our survey data shows stuff that you can't really see in lower resolution images, like all of this filamentary structure over here. I especially love these bow shocks over here, as we'll go into just a moment. Yeah, here's the same area as I've zoomed in on it. I love these features here that look like, well, what's happening is that it's thicker areas of the nebulosity that's being disintegrated or dissolved by very bright young stars out of the field of view here, mostly in ultraviolet light. There's a color image of the same area. This is a comparison between our data on the top for our survey here and the Think Binder survey along the bottom here. It gives you really a good idea of how much deeper and how much better resolution we're able to achieve with our project. So by early 2022, we had nearly completed all the fields accessible from New Mexico, and we were discussing on moving the scopes down to the southern hemisphere to complete the job. We brought in David Saliski and Arnie Hendon to help us manage expansion of the survey into the southern hemisphere. I have a full-time job, so I couldn't really negotiate all of this stuff, and it was really great for them to work with us on this. At the same time, David Saliski approached his one of his former professors, David Siminovich, about I'm sorry, another David, about getting Columbia involved in this project and help to provide a site to make it freely accessible to the public. One thing before I continue on here, is one of our ultimate goals was to replace the Think Binder survey, because that's the one that everyone refers to look for targets to image. And there was nothing high enough resolution. So that's ultimately what we want to do. We want to make it freely available to everybody so you can go, hey, what's over here? Let's find out. So we recommenced operations in August 2023 in the southern hemisphere. This is the scope moved down into Chile. By the way, I've never physically been in the presence of any of these telescopes. Here's the scopes at night. You know, it was a really great setup where they open up at night. You can watch your scope, make sure everything's working okay. See if it was clear at night. You know, the Milky Way in the southern hemisphere, which is completely alien to me until recently, is visible all night. Anyway, here's a couple of results from the southern hemisphere. Is an object called the Piran Nebula. And zooming in on it, it's a really neat. I think that's like, is that called a not a Bach globule? Anyway, a cometary globule, I think this is the term, which really is just a thick area of dust and nebulosity that's being eaten away by bright energy from bright young stars in the vicinity. Here's a really cool object in the south called Eta Carina. If you ever go south to the southern hemisphere and observe, you have to look at this object. It's amazing. Really bright, pink. Anyway, here's give you an idea of a little further afield here. Here's that prawn at the bottom left again. And in the fall of 2023, we added a third telescope to try and really get this thing done. But it took 7 years to finish the north and only 3 to finish the south. Anyway, so AP3 began operations in February of 2024. By January, working with Columbia, we went and released a section of data as a proof of concept called DR0, and that consists of 238 of the completed fields around Orion in that vicinity of the sky. It's available for download on our website. Here's the whole DR0 footprint. Popular area. Anyway, and in August 2025, the Milliman Family Foundation awarded Catherine Blundell's Global Skywatch program, the Milliman Observatories and all its equipment, who continues hosting us, allowing us to finish this project. David Salisky and Arnie Hendon's tasks are complete, and they moved on to other projects. It was really great that they helped us get these things going. Arnie helped program the southern fields and then handed it off to me, and I was able to keep it running. Anyway, in January 2025, we had data release 1 of all of the northern hemisphere from 0 declination all the way up to plus 90. Okay. And you can go on the website and download the stacked fits files and process and stitch them together yourself if you're interested. Here's the location for them. You can take a picture here or just go to our website at mdwskysurvey.org. There's a link right on the page. Oh, I'm sorry. Here, let me go back. You wanted to take a picture of that? So yeah, here's how you're able to access the data, and you know, each of the completed fields are available for download. We've updated the site now. It has better fonts. Yeah, and primary data collection finished in September of last year. After that, we evaluated that the data that we had and decided to reshoot some of the individual exposures to improve the cadence. Sometimes there was some clouds, or you know, we had haze or whatnot. So as long as we had the time, we were able to keep on working on getting better data. We reshot some 2,500 exposures, which sounds like a lot, but in the scheme of things, as you'll see, it isn't too much. So here's an animation of all the data as it's being completed. You know, every month this was a plot. And you see right here, this is when we moved to the south, and it goes way faster with more scopes, but also, you know, it's only a third of the sky versus half of it. So here's a few numbers of note. The total number of light exposures, 49,440. That's an equivalent of 686 and 2/3 days of exposure. You know, the estimated size when I get it all stitched together should be about a 60 gigapixel all-encompassing three-dimensional sphere, assuming I get it done that way. And here's just a couple of more pictures here. But by the way, I was bragging about all that exposure and whatnot, but essentially it all comes down to the final picture is a giant 4-hour exposure. All encompassing. Here's a couple of objects here. Here's a really cool way of looking at the scale of this object. Here's an object called the Pencil Nebula right up over here. And we're going to follow this for a moment here. As I zoom out, the Pencil Nebula is a small portion of the bigger Vela supernova remnant in the constellation of Vela in the southern hemisphere. Almost done. Okay. And this is Vela supernova remnant is a smaller part of a far bigger nebula called GUM-12. It's 35 by 36 degrees. Here's the bow shock that you see in the middle of that area. This is the Large Magellanic Cloud, which is one of the nearest galaxies to orbiting the Milky Way. Zooming in on it, here's the Tarantula Nebula, a couple of others in the vicinity. It's like there's hundreds of supernova remnants in these neighboring galaxies. Here's the other neighbor, the Small Magellanic Cloud. Some of the objects in here. And next to the Small Magellanic Cloud is 47 Tucanae, and a globular cluster Omega Centauri. This is what many people consider the best globular cluster in the northern sky, M13. It's not really great in comparison. Here's both of the Magellanic Clouds. Sorry, as they appear in the sky, and pushing the data really shows you that there's even more of this nebulosity in the Milky Way between us and the galaxies. Here's the object in color, or colorized, and here's another one called IC 2944. A couple of things remaining is to stitch the stuff together, finish reducing all the data and stitching it together into that final object here. So let me just hand this off to Noor, my colleague here, and she's going to tell you a little bit more about the even cooler science that they're able to get out of this.
Thank you, Sean. Okay. Okay. So I hope you've enjoyed getting to know about the history of the survey, how it started. And I hope you had a good time staring at all of those gorgeous pictures. I'm still a little bit reeling from it, but even though it does take a lot of work just to finish the observations, the work doesn't end there. We want to share our survey with other scientists, and in order to do that, there's a little bit of housekeeping that we have to do before we can let them pounce on our data and use it for whatever science they might want to use. So the best way to understand the type of housekeeping we might want to do is to put ourselves in an astronomer's shoes. What have we done for many, many millennia? Astronomers have looked at the sky. So here is one field of the MDW survey. For reference, the full moon on the sky is about half of a degree large as we see it from Earth, and one field is about 7 moons long, or in length. And it takes 4,000 of these images to fully cover the whole sky. So it's nothing to scoff at. So in our little field, we pick out a teeny weeny star. I've circled that here in magenta, and it's just sitting here on the edge of our field. Put on your scientist hat for just a second. what are some questions you might want to ask about this object? And I'll just take just one or two, even the silliest of answers. What are some of the basic things you might want to ask? How old it is? Yeah. Mm-hmm. Yes, the physical properties of it, very good. Chemical composition, mm-hmm. No, yeah.
I guess the color or whatever the like, class of star.
Yes, what type of star is it? That's a really good one too, actually. Those are some great ideas. So we might want to know something about its physical properties, how far away it is. Maybe does it change in the sky? Time domain science is a big thing these days. There are a couple of these questions that are universal to every type of astronomer. We're almost always going to want to know where an object is in the sky, and we'll almost always want to know how bright it appears from Earth. So that's something we can help other scientists with off the bat. So to answer the first question, where in the sky are we looking at? You can kind of imagine yourself lost in New York City. What you might do is look for some landmarks. Maybe you would look for the Empire State, or you would look for the Summit 1 building, or the Brooklyn Bridge even. And that's basically what we're doing with the sky. We are taking the brightest stars in our field, and we are comparing it to a trusted map or a trusted star catalog to see where in the sky we are. And by doing that, we find ourselves in the sky's coordinates. We know where we are in relation to the entire sky. And that lets us find out where our specific pink object is in relation to everything else. And that is really powerful, because then you can compare with the mass of scientific literature that has already been done in astronomy. So fun fact, that little star we were looking at is actually two stars. It's a binary system called HM Sagittae. And you might know binary stars as two stars that orbit each other. And this is a special type of subclass of binary, where you've got an evolved star called a red giant and a super evolved star called a white dwarf. So this has been an object that's been of some interest to scientists and astronomers. This is an actual image of HM Sagittae that was taken by the Hubble Space Telescope, and that is one of the great telescopes out there. So they've actually taken images of this object in 3 different wavelengths of light. The blue is oxygen 3, the red is nitrogen 2, and the green is H alpha. And what is our survey all about? H alpha. And you can see it actually seems like it's really bright in H alpha. You see these little diffraction spikes. They kind of look like crosshairs. And that's a telltale sign that something is very bright in your image. So when we compare it with the stars that we see in our data, it actually seems like HM Sagittae is rather bright in H alpha. That is the red cross that we see up here in the corner. And it also seems like other symbiotic binaries also kind of seem to stand out. They're all kind of away from where most stars sit. So that's really interesting. But can we trust these measurements all willy-nilly? A scientist has to be skeptical. So there are a few steps we can take before we can fully trust these brightness measurements. A lot of things in the sky may appear as stars, but they're not actually stars. And Sean has actually alluded to this already. So things like satellite trails and cosmic rays are real things we need to be concerned about. When satellites pass by overhead, they leave these linear trails in our images, and that's what we're seeing here. Cosmic rays kind of look sort of funky. They can appear kind of like wonky and small and elongated, but some of them could be mistaken for stars, and we've got to be worried about that. And the best way to account for these issues is to take multiple images of our fields. If something appears in every single one of our images, we can be almost certain that it's real. But if it only appears in one, that might be a good sign that it's something spurious that we don't need to be concerned about. The second hurdle that we need to overcome before we can trust our brightness measurements is we need to account for the fact that the weather changes, even within the night. Clouds might pass by overhead. There might be a little bit of dust or haze, and we try to account for this, but sometimes there's only so much one can do. So you can see these dips in brightnesses. That's these red dots over here, where our objects appear a little dimmer than usual. And it's not just confined to one or two, it is all of our stars in a particular image. So to account for this, there we go. We basically need to offset our brightnesses a little bit so that everything kind of levels out in the end. So these plots on the right over here, it's a lot more even than what we were seeing before. And that's good. So now everything is constant and stable. So we basically do these steps and then some, which I won't get into today, but maybe another time. We do this for each star in each image in all of our fields, and that ends up being, it's at least 6 terabytes. It's a lot of data that we're handling and preparing for the public. And there's a few different types of data products that we release, and it is meant to account for the fact that different astronomers might be interested in different things. Some people might be interested in time domain variability. Some may be interested in really faint objects. Some may be more interested in the diffuse nebulosity, and you've seen a lot of pictures of that in this talk so far. And some people might be more interested in the data science aspect of things. So it might seem like it's kind of a random list of data products, but let's consider all of the different types of objects people might be interested in. We've already seen a little bit of the symbiotic binaries. We've seen a little bit of the post-AGB stars, which are related to the planetary nebulae because they are at a rather evolved stage of their evolutionary life. T Tauri stars are pre-main sequence, so they're actually rather young. Cataclysmic variables, it's maybe poorly named, but it is actually another type of binary star. Wolf-Rayet stars are supermassive and are doing some interesting things, and B stars are showing these very interesting emission lines. And all of these objects have something interesting to say about stellar evolution. They all match up with different stages of a star's lifetime. And as stars evolve, the amount of H-alpha light that they emit changes. And it's really important to have a nice, complete catalog of these stars so that we can really understand how stars are evolving over time. And I'm not even going to get into it, but binaries just make it twice the fun. So to end things off, we would like to thank David Middleman for his vision that has driven this team for over a decade, and Michelle Middleman for making sure this project came to fruition. And also we would like to thank our audience for sitting and enjoying our talk today. Also, you should subscribe to Sky and Telescope.
Okay, we're gonna do a little bit of Q&A, and I think we'll bring the lights back up to what they were before, so guard your eyes. Oh, thank you, Sean. So you're welcome to ask a question out loud, or if you prefer to type it in the form, please do. We'll just take a few questions, and then I'm sure our speakers wouldn't mind if you came up after and asked them some more too. So let's have a question. Yep.
Do you plan on comparing some of your data with, like, what they're doing with the Gaia satellite and the Nancy Roman observations? Because those are also like full sky observations. Do you think your data can tie into that at some point?
So the question is, do you plan to compare your all-sky survey with other ones like data from Gaia or soon the Nancy Roman telescope?
So we actually do already use a little bit of the Gaia data. That's actually the trusted star catalog that we use to figure out where objects are. Gaia is really good at figuring out where things are in the sky. No, yeah, and it did it pretty well. So we're actually already using Gaia data. As for the Roman Space Telescope, I don't think at least I haven't thought about it all that much.
It launches in
Right. And
what, autumn?
I think it's the end of August. Yeah. So it's getting there.
Okay, you had a question?
Yeah, this is not very specific, but so each field is taking that different time, and the sky is not static. So conceivably, what might happen is we finally stitch things together. We might have two adjacent fields that disagree on what happens at their overlap. Does this happen? How do you?
So since you take the exposures of different times of year, you talked about like the winter Milky Way and a summer constellation, what happens in the overlap if it's different times of the year?
Nothing, actually, because we're not at an image scale where you're really going to see much difference in like star positions, okay? I was hoping there's half a dozen stars that in 10 years I would be able to detect like parallax, some movement of the stars. Unfortunately, like the most famous is called Bernard star. We ended up getting all of our data in 2 weeks of that one. So there are some that have actually a baseline of 10 years on this, but unfortunately there isn't many moving objects that are showing up in that. We're just not at the image scale that it's going to really be a factor.
But conceivably, if you were to do this in much higher resolution than
Oh yeah, you know, like I was saying, with that specific star, Bernard star, it moves an appreciable amount a year. You can see its movement 1 year to the next. In perhaps even in our data, it would have been possible, but it just didn't happen to work out that way.
Go ahead.
Did you ever say what hydrogen alpha is?
So can we get a definition of hydrogen alpha, please?
No, yeah. So hydrogen alpha is, so if you're familiar with, I guess, orbitals in any sense, it's the photon of light that's given out when it moves from like a n equals 3 state to an n equals 2 state. So I think when it gets de-excited, or when really ionized gas starts to cool down, it emits H-alpha light. And that's why it's a really good tracer for, you know, what's happening around really, yeah, exactly. Like yes, that's right, that's right. Like if it gains energy or if it loses energy, and in our specific case, it's losing energy. It's going from a more excited state. Exactly. It's hydrogen that starts to cool down. Like very ionized hydrogen, when it starts to cool down, that's when it starts to release.
Right. Exactly. What we're doing is we're using a filter that narrows only the passband of light. I'm sorry. Oh, I'm sorry. So we were using a filter that only looks at a very narrow slice of the spectrum. Actually, only 3 nanometers of, or what was that? 3 nanometers is how many angstroms? Remember when we mentioned angstrom earlier? That's what I was trying to translate. Anyway, Yeah, it's like 600 or 300. Yeah.
All right, I'm going to end with one question online. If you could both quickly say what your favorite object from the survey was. Pick only one.
I'm going to say the Large Dimensional Atlantic Cloud.
It's okay to have the same favorite one. Okay, I cut the questions a little short for the sake of time, but I'm volunteering our speakers to answer a few other ones after our raffle. But let's give another round of applause to our fantastic speakers tonight. All right, Nora, if you'll advance one more. If you'll advance one more slide. So we have a raffle. If you look at the seat number, usually these are used to assign seating for an exam. We use it for fun. I have a random number generator. I'm going to read through it. So if I call your number, please scream it out loud, or otherwise I will give away more prizes than I have with me. All right, F14, G6, N16, B9, H13. All right, we've got one. E8. Okay, we've got two. B6. Well, we're going to count it. I13. O15. B12. Got a lot of B's tonight. All right, those are our four. Okay, thank you all so much for coming. We hope to see you in July. If you want a raffle, come see me before you head out. Thank you all so much.
What'd you guys get out of dinner?
I went to the bathroom and I came back and everything was gone. And it was like, they're lost. And you can see them down the road. I'm like, it's sort of all my house. I almost couldn't get inside the gate. I just like powered through and the guy's like, excuse me, ma'am. And it was like, Catherine! And she stops and she comes back and she like grabs me and she goes, she's with me.
I was like, I gotta be close by. Just in case.
Or maybe you should
You want one? Three examples?
So you said that if something is that negative, it's emit really cool. And are you using hydrogen alpha because that lets you distinguish nebulous stars or filter stars out?
Yeah.